Here we go. So, we did the poll, did the quiz, paired discussion. So, here's what I'd like to know. What did you, I'll make it bigger, process. So, last night when you're working with R5 and R6, let's use hands. Good, you're using hands. I like it when people use hands by default. What did you learn about the process? Valence.
Nora explained to me very helpfully that I can't skip the potential rational zeros step.
That's the entire key, the whole thing. That's good.
And
Yep.
explained how to synthetically divide. And that you need to factor, which I guess I was kind of skipping and just setting equal
Must
to 0.
factor. Okay. What else did you learn about the process last night? Solnit, then Andy. Solnit, did you have one? No?
No,
Andy.
Okay, like,
Yeah?
if you make a little mistake, you'll generate something, so
Can cause a spiral of doom. Okay, got it. Next. Yes, it can. Little time, like you miss one negative, so boom.
Yep.
Nora, yeah.
Yeah, remember to take the right sign.
Remember to use the right sign. Yeah. What else? There and then there. Yeah.
I thought it was kind of useful to, when you have a cubic equation, just simplify it in the beginning, simplify both.
Start by simplifying. Yep.
And then you,
Yep. Simplifying. I can't even spell simplifying. Simplifying. There we go. Good. Any other things? Yes, Solnit.
it's time-consuming.
Time-consuming, yes. And
Also,
the only thing that
what do you
makes...
mean by
Yeah?
simplifying?
What?
Like, just, is that the factoring or the simplifying?
Yes.
Because it's helpful, because if you factor and you get something in the numerator...
To simplify, you need to factor.
Yeah, but like if you get something that is like a factor that's both in the numerator and the denominator, you need to know that for the steps.
Yes,
That
the
would
steps
work.
aren't entirely linear. What they're telling you is that if you factor first, which is a step in
Okay,
simplification. Yes.
I was just thinking,
And how do you make it?
factor for-
In order to make this process less time-consuming, does anybody know what you need to do?
do it all.
Danilo.
Practice.
That's right.
Anybody tell you that I miss practice? If a coach say I miss practice, and y'all hear it, then that's that. I mean, I might have missed one practice.
Practice. That's correct.
Not the game.
What did I do?
Not the game. Practice. The only way. What part of the process is most time-consuming?
Practice.
Practice.
Yes. Hopefully you spend most of it factor. But what part of factoring is? What part of synthetic division? Guys. Hi. I'm over here. Stop. Because what happens is you get into this recursive loop of being behind, which causes you to talk more, and it's not just you, it's everybody around you that gets distracted by your, nammering, okay? Got it?
Yep.
Just catch up later. Yeah, it's the potential rational zeros, it's testing. Testing PRZ. And you will get better at that as you practice. Okay, so let's talk specifically about R5 and R6. Let's see how you did. Yeah, sure.
You said start by testing the
Small positive one.
Is
Small
there a
hole
point
po-
where it's
small hole
easier to
positive.
just, test the negative ones?
Sometimes, yes, you'll get it. You'll have intuition about it. You'll look at the coefficients and you'll have intuition about it. But get the easiest ones out of the way. You can test them 2 seconds. Every zero has an equal chance of being a zero.
Yeah.
At this point in the process. So, can someone tell me what the factored form of the numerator in R5 is? Someone raise their hand and tell me. Mariah.
Is that only factor?
Top form. Yep.
Okay, so x minus 2,
Mm-hmm.
x plus 3, x minus, plus 1.
Who agrees with that numerator? Raise your hand. All right, you're popular today. Congratulations. Who wants to do the denominator? Solnit. Next. Anybody else want to tell me?
-1,
Oh,
+5, and
that's not what I asked.
3.
Fowler.
X minus 1, x plus 3, x plus 5.
I want you to speak precisely.
I'm sorry.
Who
I
agrees with that
find it
denominator?
on my zeros.
Yes, I understand. What's your favorite color? A pony. It doesn't work, okay? The pony might be your favorite color, but that's not a proper answer. Do you understand? That's right, I'm the king of cognitive dissonance.
Well,
Anyway,
I was raising my hand for
I
something
know
else,
what
so
you were
really
trying to do.
clear, and then you called on
this
me.
is, I'm great, I'm glad this is on record. This
all
is
very
amazing. We're totally going to remix this class at the end of the year. So what cancels Solnit?
X plus
X plus 3.
Yeah, it cancels. Okay, can someone tell me what are the vertical asymptotes? Someone tell me right now, just what are the vertical asymptotes? Someone tell me. Hammer, what's one of them? Yes. And what's another one of them? Andy? -5. This one correlates right there. And this one correlates right there. Exactly. So now, can someone tell me what the x-coordinate of the removable discontinuity is? Someone who hasn't spoken yet. Danilo.
It's 1.
No, what's the x-coordinate of the removable discontinuity?
The exponent?
Yes. What did we cancel?
Okay. Oh, it's 3.
Not 3.
-3.
Yes. And then how do we get the y value for -3? Someone else tell me. Someone else tell me. Furia.
Put x into the equation.
Into the equation. Which one?
X minus 2.
Yeah.
X plus 1.
Yeah, the simplified R5. So you want x minus 2, x plus 1 all over x minus 1, x plus 5. And we can do that because what's the difference between this one and this one right here? The only difference. One's a hole, one has a hole there and one doesn't. That's it. So we can plug that into here and we end up with -5/4. So that's where there's an empty dot. Is there some crazy, weird functional behavior there?
Got it.
No, it's a removable discontinuity, so just it's traveling along, it gets to that point, it goes open dot, and then it keeps going. What do asymptotes do? You get some weird spiky stuff, right?
Yeah.
Everybody do it. We go up, down, like this, right? Moving on, let's talk about R6. Can someone tell me what the numerator of R6 is? Numerator of R6. Someone who hasn't spoken yet. Someone new today. Someone new. Yes, Hector.
Is x minus 5
Yep.
times x minus 3
Yep.
times x plus 2.
Yep. All over. Who wants to do denominator? Dawan.
X minus 2,
X plus what?
And you guys all found that by using...
Potential rational zeros. Same process over and over again. This cancels, so can someone just tell me what the vertical asymptotes are on this? Someone raise their hand. Gare. And hold on, balance. What's the second one?
1?
Nope.
-1.
X equals -1. X equals -1.
Okay.
The vertical asymptotes are the imaginary vertical line that they can't cross. Can someone tell me what the removable... Well, do we agree with that? I think we do. I don't hear any major complaining. Removable discontinuity in this case? Hammer?
3 minus 5.
Yes, 3 -5/2 is correct. You know it's 3 because that would make that factor 0, 3, and then you plug 3 into the overall equation after it's simplified, and you end up with -5/2. -5/2, yeah. Does that make sense, everybody? Pretty good with this? So far, domain, intercept, symmetry, vertical asymptotes, and removable discontinuities. Okay, so let's transition here. Take out, yes. Yeah. No, the domain, stop here. Don't cancel. The domain of this, the actual domain of the function is x does not equal 2, 3, -1. That is the domain. Two of them, this and this, these are vertical asymptotes. And this is a removable discontinuity. That is the domain of the entire function. We're going to transition now. Please take out the bean counting lab that we haven't talked about yet. Can someone tell me what it means by doubling time? Fowler, what's it mean?
How many generations it takes for the population?
To double, yeah. I looked at it at first, and I was looking at it in terms of calculus. Like, maybe you need to take a derivative and calculate the rate of change and model the first point of it. No, you just look at what's the initial generation 1. What's the population?
10.
Generation 1 is 10. So you want to know at what generation does it get to 20? And it depends on your data set. What did people think about what?
4.
About 4. 3 or 4, depending on what your...
Exactly 3.
Yeah, it depends. You guys had an aggressively, unbelievably fertile population. Yes. When did it get to 40? Anybody? Like 6 or 7. Like 6 or 7. And then what about? And then we didn't really get that far because it takes too long. It's about, you think, maybe 9 or 10. Now the question is, what's the doubling time? The doubling time in this case would be 3 generations. And then it becomes about 2 to 3 generations and about 2 to 3 generations. What's interesting is that it's either, the doubling time is either what or what? Doubling time is either staying constant or what? Or, well, I don't think from this information you can't generalize that. Or increasing a bit. Now, any increase you see probably is due to what? You're doing the same thing every generation, right?
Yeah.
Yeah.
Wait, you're saying the time is increasing?
We're saying that the time it takes to... No, so the time it takes to double would decrease. So they're breeding faster, okay? Now, here's the thing. I don't know if you saw this. I took the spreadsheet and did one kind of neat thing with it. Yeah, Alan's going to blank everywhere. I'm going to try to put Allen Iverson into every test we have, okay? Here's your data sheet right here. And then I had it auto-average the generations. And then I had it graph the data as it was put in. So you get this nice curve, actually. It works out pretty well. And if you actually take this data, this is the group data right here. If you actually take this group data, so this right here is the group averages. This is across all three classes, by the way. Group averages. It works out to about every two point something generations. It'd be how many? You'd have to do this out a whole lot to get a nicer data set. Mainly because even with only 15 groups, there were some outliers. Some people had unbelievable luck at flipping tails, so their populations were like decreasing for a couple generations, which does happen, but not that often. It doesn't happen that often. It happens about the same as increasing wildly. Okay, so the second question asked for you to actually use expreg. You needed to use expreg on your data set. That's what you're supposed to do. Who has an equation for me? Who has it? Brooke, what do you have?
Y equals
Yep.
3.587
Yep.
times 1.4. Yeah.
1.4 to the x. Anybody else have a different one? Anybody else have a equation? No one else got an equation. No one else did the homework. Andy, what'd you get?
Y equals 7.5
Yep.
times 1.3 to the x.
Yeah, I'm generally seeing more like 7.5, but it completely depends on your data set. Completely depends. Completely depends on your data set. I think I did it out on the calculator here.
For the average?
For the average. I did it out. We did it on one of the other classes. We don't have to do it again. And let me just change the mode here just so you can see it. It turned out to be... Sorry about the screen. It's having issues today. Let's just do stat, calc, expreg is... It's down here somewhere. There it is. We do expreg. The average comes out to this right here, 7.6 times 1.3. I'll clip this in. But it depends on your data.
Mine is close to 7.
What's interesting though is the reason I did this is I wanted to see how our averages compared to the actual data set modeling. To see what the variance is like. So according to your model, what will the population be after 300 years? So how many generations is that? 15 generations.
Yeah.
Now, do you have your predictions? What you think it is? Danilo, what do you think it is?
586.
Okay, anybody else?
765.
765, Mariah. Yep, good. These are good. This is about exactly the type of the same type of numbers and spread that we got in B block. C block had some really strange numbers. If your data set is really strange, what happens to your long-term projections? They just blow up, especially on an exponential model. They blow up incredibly. Now, this predicted, I think, a little lower. Let me see here. This one predicted, so if I actually want to do this out, I wanted to do y1 at what? y1 at 15. 473. But are these at least in the same relative area? Yeah, I mean, it was strange if the answer was something like 113,000, which we did before, right? Remember when we had quartic models that spiked way up when it was supposed to just go up gradually, and we'd get into like 68 billion or negative something? Always check reality. After 15 generations, would it make sense if there was a million of these things? No, it would not. Okay, so moving on, let's go to 3 here. These are good. I like these questions. These are great questions. So it's asking on this one, what are some assumptions of activity? What are some assumptions of this activity that you think accurately simulate human population growth? What do you think? What's one assumption, Mariah?
That it sort of does the gradual incline.
Gradual incline. Yep. Anything else? Any numerical ones? Yeah, Andy.
Well, any for our set of data.
Yep.
The deaths were actually okay.
What do you mean the deaths were okay?
Well,
Deaths
we
are
still saw the exponential value.
Oh yeah, still saw EXP growth.
Yeah, the probability works.
with that. No, yeah, what do you want to say about that, Solnit?
The probability looks like it worked out so that the graph is fairly accurate.
Now I have a question about that. How do we know that this kind of growth rate is accurate to an actual population growth rate of humans? Think back to the video we watched. What did it tell you? There was a number it gave you in that video that was really important. Do you remember the number 2.1?
Yeah.
That's the, what is that? That's the replacement rate you need? That's the replacement rate. Well, that isn't a replacement rate. That's the fertility rate you need
To keep the fairly stable.
for a stable population. Now, the real big question is where does that 2.1 come from? That's a really interesting question, but that's not something we're going to get into. But in this case, whenever a family has babies in our model with these beans, how many babies did they have? 2. They had 2. And then that family was taken out of the parenting pool. Yes, it does. Yes.
Sounds like what?
The giver. Yeah. Okay. What are some of the assumptions that do not accurately simulate human population? 1, 2, 3. Let's just go around like that. Go.
It doesn't account for any natural.
Yeah. Doesn't account for any threats to equilibrium. I'm trying to make that as general as possible. What else? What else? Yeah. So yeah. Yeah. I thought we could do it as a whole, and then I could randomly throw out like events, like bubonic plague. Danilo, go.
I think that it's in the beginning it's realistic that it grows, the rate of growth is high, but in reality it's logical that it stabilizes by time, and it doesn't in this case.
It doesn't. Yeah. Doesn't account for a carrying capacity, right? That's what you're saying. You're saying there's no ceiling that it's slowing down towards.
Unless you run out of beans.
Or unless you ran out of beans, exactly. There's your carrying capacity. That's right. That's actually a really good. That's a good point. Yeah.
I thought you should go with that, and then if you knock your cup over and beans fall out, they're
They're
gone.
dead. Yeah. Any other problems with this model?
I was just gonna say.
Yeah.
When that video we watched where it was a really cool model.
Yeah. The circular population modeling.
It did show that it was going to start. It was going to reach a high point and then maybe even start decreasing.
Well, the rate is that model didn't predict a decrease in population. It increased. It's going to stabilize.
Right.
So it looks like it's going to stabilize in 2050 at around like 9 billion people. 9 billion. But we're in the last billion where it's going to happen this quickly. Yes.
But did it say that the population would eventually start decreasing because not eventually, because the generation that was having kids would be larger than the last.
Yes. Okay. So that's true. Yeah. But the idea would be when a population levels off, it doesn't mean it's like exactly this. It usually oscillates around the carrying capacity. It goes below. So oh no. Okay. It goes back up. No. Down below. Prosperity. Overpopulation. Peace. War. Yes.
I'm not sure if it's related.
No. It's fine.
What causes fertility rates to go down?
That's a really big question. Now, they gave you an example in that video. Do you remember what the example country was? The one that had the sharpest decrease in fertility? No. What country?
It's China.
Nope.
No, Baghdad or
It was Iran.
Iran.
It was Iran. In the 50s, the fertility rate was like 7.5, and now it's like 2. So what things in Iran have directly affected the fertility rate? Not birth control. What? War. Has anybody like war, conflict, countries that have gone from incredible prosperity to incredible the opposite of prosperity, chaos. Has anybody? I saw this very interesting. I gotta find it.
Generation, the only option was birth, or is that?
Yeah, exactly.
There
Thank
was
you.
no going to be the next generation from the future.
So what doesn't it account for? What about people that?
Life expectancy.
Well, that too. Yeah, we'll get to that in a sec. What about people that don't
Don't have kids and don't die.
that don't have kids, or for whatever reason? In our model, each kid turned into a viable, productive producer of the next generation, right? Is that always the case? No.
People were born sterile.
Maybe, yeah, people want to or choose not to have kids, right? I mean, there's lots of different reasons, or live forever, apparently. And also life expectancy. Yeah.
21 years they had us.
Square.
Yes, x plus 1 squared. How about this one? In round 1 here. Here we go. Andy, yes. Andy, what is it?
Let's see.
You can phone a friend.
Mr. Seamon, what
Yeah, did you what is it?
the 5x
Yep,
plus 1,
yep.
5x
Squared. Good job. Okay, next one here. 4x squared plus 4x plus 1. Dimitri, what is the factored form?
2x
Yep,
plus 1
yep.
squared.
Yes, good job. Okay, let's go with 9x squared plus 6x plus 1. Corso, what is it?
3x plus 1.
Yeah, there you go. Noticing a pattern on those. Yeah, here we go. How about this one? 1x squared plus 5x plus 6 equals... Baker, what is it? 10, 9. Pressure's on. Battaglia.
call a friend.
X plus 1 and x plus 5.
Yeah, there you go. Good job.
No.
No,
X plus 3, X plus 2.
Ooh. You fail. You've been voted off the island.
Don't worry, Dave.
Most boring show ever.
What, lost?
No, I was just math survivor. Here we go. Hannah.
Oh no. X. Plus
Shh.
8 x minus 1.
There you go. Very good. Good job, Danilo.
Thanks, Danilo.
Okay, here we go. X squared minus 7x minus 8. Hannah, again.
Thanks.
Go.
X minus 8x plus 1.
Good job. All right. Moving on. Zach Cochran. Hey, it's really hard to do what I'm trying to do right now. Okay, go.
X plus. Wait, hold on. X plus.
Danilo.
2.
No, X plus 4. And then X minus 4.
Yes, good job, Danilo. And he can hear you at about 1/10 the decibel level, Hannah. Okay, ready to move on to the Funland? Funland, here we go. You can use a pencil, and you have 10 seconds. And I'll call on you at random. 10, 9, 8, 6, 3, 2, 1. Brooke Fowler.
3x
Yep.
plus
Okay.
x plus 4.
Nope. X plus.
1.
Good job. All right. Okay, another one. 15 seconds. 14, 12, 9, 8, 7, 4, 2, 1. Yep. Solnit.
3x.
Yep.
And x.
Yep.
And after that, it would be
Phone a friend.
4 and 2.
Plus 4 and what?
Or
Does that work?
No.
I don't
No.
know.
It's minus 4.
Yeah.
It's minus.
Okay. Minus 4 and what?
Getting out of
Is that good?
Yeah.
You care about factoring. I like this. This is nice.
Oh, yeah.
I love factoring and studying.
Yeah, that's
3x squared plus 6x minus 4x minus 8. Yeah, it works. Woo! We're having fun. 3x squared plus 10x minus 8. Who has it for me? Who has it? And we'll go with Gare.
I did it. 3x and x.
Yep.
And also, the other terms in the factor
Yep.
are minus plus 5 minus 3.
Nope. Got to multiply together to get negative 8. Phoning a friend. Cochran.
3x minus 2 and x plus 4.
Yes. Good job. So let's go with, yeah, it works. Let's make it more fun. Ready? 15 plus 2x minus x squared equals 15, 14, 13, 12, 11, 10, 9, 8, 5, 3,
You count funny.
2, 1. Danilo.
X plus 3
Yep.
times negative x plus 1.
Who got that?
I got it the other way.
You can put the negatives. Yeah, you can put it in different places. That's fine. Okay, here we go. We're going to keep on moving towards even more fun. I'll do one last one here. 4x squared plus 3x minus 1. 10 seconds. 6, 7, 8, 9, 10, 5, 1, 2, 4, 3. And we're going with Dawan. X minus 1. Who got that? Opposite, like this?
Yeah, minus 1 plus.
Minus 1 plus, like that?
Yes.
Good job. Okay, we got a few more to go through here. 4y squared minus 16y plus 15. 15, 1, 14, 2, 13, 3, 12, 4, 5, 11, 6, 10, 7, 9, 8. David, got a guess? I love this game. Okay, anybody? Oh, Furia, go.
2y minus 5.
Yep.
And 2y minus
Who got that?
I know.
So, once again, how do you get it fast?
You talking about practice?
And with that, we're going to talk about what you have for homework. Wait, homework here, okay. Your homework, everybody, your homework. So, I want to copy this in. So, for homework for E-Block here, you have 3 things. The cubic equation, we'll talk about it. If you already brought it in, you're already done. But if you didn't find it, practice factoring. I posted a big sheet of things you can practice. You can choose as many or as few as you want. Right here, I have it posted in your homework. It's listed as homework 6. It's like 85 different things you can practice factoring. Watch Rational Functions Part 4 and bring in at least 2 questions. We're done with Unit 2 once we finish Rational Functions, and we're about to be done with it. The big point is that we're going to be graphing these soon because we have one last thing to learn about. Well, 2. Horizontal asymptotes and oblique asymptotes. And our Unit 2 test will be on Friday or next Monday. Go home.